Good morning, everyone. So, I'm Dr. Senthil Kumaran. I'm from Additive Kancheepuram. I actually wanted to talk to you today about additive manufacturing. Additive manufacturing is one of the very interesting topics as of today because it is part of the fourth industrial revolution. So, before I go on to introduce the topic about what we want to do today, so I'll just tell you briefly about the present situation right now we are facing. So everyone is forced to stay at home, not to basically socialize with each other, even if you want to socialize at the distance of 6 feet. So we have been constrained to basically move around and then touch surfaces, greet each other. So we are going through an unprecedented situation of I would say what we call as this pandemic. So 3D printing community has come up to help. So what we call as this, PPPs, personal protective equipments, and design of new ventilators. So there's a lot of activity that is going on in 3D printing. So I would like to touch upon a few topics today. So I'll just quickly go to my presentation. So I'm Dr. Senthil Kumaran. I'll introduce myself and what I do with the help of a presentation. So, yeah, I think hope all of you can see the presentations right now. Yeah. So if one of the things that we normally do in our lab is like we have been designing a lot of products for product development as well as for testing products. So today I'm going to discuss few introduction to design for additive manufacturing in general about additive manufacturing because many of you may not have introduced into additive manufacturing. So mainly I'm going to talk about the designs, the new product designs that have been designed for COVID-19 to fight against the pandemic and things like that. So before I go, I would like to quickly introduce my institute. So, our institute is an Institute of National Importance established by MHRD. So it was initially mentored by IIT Madras from 2007 to 2011. And we are currently operating from our permanent campus in the outskirts of Chennai. So we have 14 academic programs, mostly design and manufacturing specialized. And then we are also at the intersection of IT and manufacturing hub. So we do a lot of work in relation to the industry. And we also have expertise in IT focused research in manufacturing. And we have interdisciplinary research groups in cyber-physical systems and smart manufacturing. So this is the basic introduction about our institute. So I want to introduce my lab and what we do and things like that. So our lab is called Design for Additive Manufacturing Laboratory. So I'm the lead for the lab. So we have a few members who are working on additive manufacturing as well as smart manufacturing. So mostly we do work on 3D printing as well as polymers as well as metals. And then we are working on distortion prediction, resources prediction, and also on design for additive manufacturing. So what is design for additive manufacturing? Is about the way we conventionally think about design. Um, is like one of the things that we do about conventional manufacturing is when we design for something for additive manufacturing, we also do conventional manufacturing. When you are moving from conventional manufacturing to additive manufacturing, we have to introduce a lot of design variations and things like that. So, and if you look at the academic programs, I'm also working as a division leader for smart manufacturing division. So smart manufacturing division is giving, offering two programs in BTech as well as MTech in smart manufacturing. I'm also doing a lot of outreach activities for training faculty. So I'm also the coordinator for Teaching Learning Center. It's funded by MHRD. So that's one of the outreach. So this is my research and teaching and outreach interests. Okay, so looking at the AM ecosystem, so additive manufacturing has been there for a very long time, last 30 years. Initially, it was only for prototyping, only polymer parts, and for the last 20 years, people have 3D printed metal components also. If you look at the overall 3D printers ecosystem, you can see there are polymer machines, desktop machines, and metal machines, ceramic machines, and also printing of electronics and things. And there are these are design related issues, which you can see here. So, and we also have material issues like processes and AM ecosystems. So we have been looking at this systems. One of the systems is like, what we do in one of the systems is like we try to basically understand, the understanding of the entire, like let's see, for example, if you want to, like, put this, so just put the PowerPoint presentation first. I think there is some issues with the PowerPoint. I think you can see the screen right now. Probably. So yeah. So we have been, we have materials, we have some, related issues. For example, additive manufacturing is introducing a lot of new materials. Every now and then we have seen, materials being introduced into additive manufacturing. Initially, it started with polymers, very few materials capabilities, and then when the powders become pervasive, we polarize many powders, and then we can use them as part of the additive manufacturing materials. So there are many different types of processes. Let's say we have processes which are laser-based, process which are electron beam-based, process which squeezes materials through a very small nozzle, process which actually jets the material, and then there are processes which welds, micro welds them together, like ultrasonic consolidation. So there are many different processes. So in today's topic, I'm not going to discuss detail about what these processes are and how these processes are classified and nomenclature and all those things, because ASTM has classified into many different types of process. But in general, we see that there are processes which are binder jetting, there are processes which are powder bed fusion, and then we have the material jetting process, we have process like direct writing, we have direct metal deposition, and then also we call the process something like consolidation, or sheet metal lamination, and all those kinds of processes. So there are a variety of AM process. And if I look at that ecosystem, there are people who do design for additive manufacturing, develop novel materials, and also develop new processes, and also optimize the existing process, and also develop an understanding of the process, like science behind it. So if the process could be very well useful, let's say, for example, to predict the failure of the parts. For example, in powder bed fusion, the parts may fail because of delamination, it may because of distortion, and so many things. So the science can predict these kinds of defects upfront, so that we can get the first part right. So that's the idea of science prediction tools and things like that. So in general, if you look at the overall ecosystem, this is the commercial ecosystem. We also have material suppliers like polymer suppliers, metal suppliers, and things like that. Recently, a lot of research groups are very active in additive manufacturing. Okay, so before I go into this COVID-19 situation, how 3D printing helps in COVID-19 situation, I would like to tell you about why additive manufacturing is introduced into the fourth industrial revolution. Now, one of the major applications of additive manufacturing is in medicine. Not right today, but it has been there for the last 20 years. One of the niche applications of additive manufacturing is the medicine. For example, some of the cars that are produced, very long back, like 1850s, they are craft production. It means you have large varieties of parts. When the second industrial revolution came, then there was the manual production, and then it peaked around 1955. But in 1980s, the era of mass customization started. The mass customization is about customizing to individual. For example, you have an implant, you can customize to an individual. And also, if you have, let's say, for example, a shoe insole for a diabetes patient, it can be customized to an individual. So the reason why additive manufacturing becomes a niche application for medicine is because you can take the geometry of a patient and customize that for the particular individual patient. For example, you can take measurements and you can actually, custom made one part through additive manufacturing. But the reason is why not a conventional manufacturing process be also used. The major difference is in a conventional manufacturing process. Let's say if you are trying to basically produce different custom parts, let's say different varieties of parts, the problem is like you have to use either a die, and then injection molding if you're doing injection molding. So for every design, you have to make a new die. So die is very costly unless you make, let's say, 10,000 or 1 lakh parts out of the die. So essentially, you are going to not going to get the cost amortized for its value. So injection molding for custom parts is not economical. Whereas additive manufacturing is not economical for mass production as of now, but it is more economical, let's say, from the cost viewpoint, for custom-made parts. Like you have different varieties, like 100 varieties can be made in one single go. For example, some of the applications which involves hearing aid shells. So, for example, there are in the canal hearing aids, which helps people with difficulty in hearing. So they could be completely enclosed inside the ear. We call this as in-the-canal hearing headsets. So that can be customized. 100 patients geometry can be captured in a day, in one single day, and all the 100 parts can be made in a single night. So tomorrow morning you can deliver the, let's say, the hearing headsets very easily. So this is the kind of, I would say, what we call as the power of additive manufacturing. That's the reason why we call this as fourth industrial revolution. Even though additive manufacturing evolved over 30 years, now it is becoming revolutionary, from evolutionary to revolutionary, primarily for the reason that it can actually customize. That's what we see here as the customization. And mass manufacturing is more adept at volume, whereas additive manufacturing is really good at customization. But it can get really good at volume too in a very short span of time. Maybe in another 5-6 years, it can actually even make large volumes of parts. And another important thing about additive manufacturing is complexity, because I said the fourth industrial revolution is about decentralization, distributed, personalized manufacturing of complex products. So that is the reason. For example, decentralized. Right now, one of the problems that every country faces today, especially under the COVID-19 situation, is because the factories are situated in China. Now, let's say, for example, the origin of, we don't know, it still could be debated. Right now, everyone believes that the origin of COVID-19 is somewhere in China, the Wuhan province. But you see, most of the factories are also situated in China. So the global supply chain is entirely disrupted. But people could be able to make in their own backyard, just because additive manufacturing machines are there. Because of the maker culture in the US and other nations, even in India, people are able to basically make these devices at distributed locations. They don't have to import it from a country where the factory is somewhere located. So they were able to decentralize the manufacturing and distribute manufacturing. And also it's personalized. For example, if somebody has a different size, so you can actually cater to the different geographical distribution or anatomical characteristics of the individual who is using it. So if you see, for example, it is customized for the individual. And another important thing is complexity. So most of the products that right now we use are very complex products. So the complexity, not just from the geometric complexity, but functional complexity, as well as, we have different types of complexities, material complexities and things like that. So additive manufacturing is adept at handling this. So additive manufacturing, enables all these aspects. You can decentralize the production, because you can have a 3D printer at home and you can make it. You don't have to wait for a part to arrive from China. It's distributed. Probably you can make some parts here, some parts in the neighborhood, and then assemble them together. You can distributedly manufacture it. Design may be done at one place, but you can make them in, instead of making in one factory for the world, maybe you have several factories distributed across the world and make it. And also you can customize and personalize. That is another major benefits of additive manufacturing or 3D printing. And also it enables complex products, manufacturing of complex products. So that's the reason why we say that additive manufacturing actually can help in doing this. That's why additive manufacturing becomes a very important tool for fighting the COVID-19. So as I said, our group works on design for additive manufacturing. In design for additive manufacturing, what we do in our lab is we take an existing design and then we push the design into this particular area where the complexity comes free. For example, for conventional manufacturing process, when the complexity, geometric complexity increases, so what happens is that you have, the cost gets skyrocketed. So essentially, we want to reduce this cost. So additive manufacturing helps us to basically reduce this cost. So the complexity comes free. That's the reason why we have the additive manufacturing and the conventional manufacturing intersects at this point. We call this as complexity break even, where we are pushing the designs to more complex so that we get the benefit of this cost. So this is the complexity. And if you look at the benefits of such a complex, product manufacturing, is you can have internal walls or ribs, you can have wall thickness combinations, you can have freeform surfaces, you have large aspect ratios, you can have variable radii. So you can see there are a lot of geometric complexity that can help you to make parts. And there are also hierarchical complexity, like you can make honeycombs, irregular porous structures, low wall thicknesses, surface textures, and mesoscopic structures. These are some of the hierarchical complexity. And you can also make parts with material complexity, like continuous material transitions and different parts in one parts. And you can also have different parts that can be embedded. Probably you can make an electronic circuits embedded into the parts, or you have functional extension of the part. So you can actually make a lot of sandwich designs without joining operations like snapfit and living ninja, all those things which is possible. And you can also consolidate many parts into one part. You don't have to make a very complex assembly. So you can reduce the number of assembly operations and then consolidate the parts together, and then you can functionally integrate the parts together. So that's how you can actually it is very easier to assemble, and you also use less amount of material because your consolidated parts and your joints becomes less. So a lot of applications of functional complexity is there, and the major benefits is cost reduction. So you can see the assembly cost, logistic cost, quality, manufacturing, maintenance, material, and development. Every cost gets reduced, and also in turn there's an improvement in sustainability. Sustainability is about the emissions to air, water, land, on energy use, material use, as well as the water use, freshwater withdrawals. All those gets reduced because of using distributed manufacturing. Right? So because your transportation cost gets reduced and things like that. And also there are a lot of higher additional product value. For example, you can improve the ergonomics. You can have very complex shapes. You can reduce the weight by having the porous structures and things. You can also improve the functionalities like damping, heat transfer, isolation, energy absorption. All those functional characteristics can be embedded, even lubrication. And also there is a reduction of design space. So there's a lot of opportunities there in reduction in the design space, and also improvements in the inner flow dynamics that is also possible. So you have a lot of efficiencies coming into play in the design for additive manufacturing. Okay, so what we do is in our lab, we do many things for design for additive manufacturing. For example, we use part consolidation tools where we reduce the part count for ease of assembly and simplify the product design. We also do lightweighting, where you can introduce lattice structures and structural optimization. And heterogeneous modeling is about modeling multi-material gradient structures. We can model generative designs where the output is optimized for material space, layout subject to the manufacturing constraints. We can have design which are repeating structures in different scales like micro, meso, and nano scales. And also we can topologically optimize geometries where we can optimize the material layout for a given set of loads and boundary conditions. And also we can combine both additive and subtractive conventional manufacturing together and model geometries for that. We can have multi-models and multi-materials and shells and colors and things like that. So we can integrate many functions, and we can also customize. For example, design of personalized products and other medical related applications are there. Right, so we will now move on to this application of 3D printing in COVID-19. So for example, COVID-19, the situation you must be knowing that it's a pandemic. Initially it started as an epidemic, and then it has moved to worldwide. It has spread predominantly through people coming in close contact to each other, maybe touching a surface or touching each other, or maybe hugging each other, or maybe sneezing in front of somebody. So essentially, there are multiple situations where people need to use personal protective equipment. So, for example, there are health workers who treat the COVID-19 patients. They essentially has to use a lot of personal protective equipments. For example, they need to use a mask, and they use goggles and gloves, face shields, shoe covers, and the entire suit. Because sometimes it looks like a bunny suit, but still it protects them against the virus spread. So, for example, the infection can happen by either touching the points where the infected person touches it. We call this as a fomite. For example, let's say you have a hand, you touch the particular surface where the COVID-19 patient has touched. For example, there is an infected person, the COVID-19 positive patient. Probably he touched a surface. You know that there's also a lot of introductory material available, how to basically prevent the spread of COVID-19. One of the very important things is to wear personal protective equipment. For example, wearing masks in public places and maintaining social distance, and cleaning the public places, touch points like lift buttons and door handles. They have been the major spreaders. For example, some of the super spreaders predominantly happen through even sneezing, coughing, and without use of the mask, if it can spread through air. So we know that starting from January 1st, where it got accelerated the spread. So mostly because of the non-availability of such personal protective equipment, we can see in many Western countries it spread like a wildfire. So the infection started spreading very rapidly. You can see the curves. So we have been hearing this term called flattening the curve. Many countries are struggling to flatten the curve, primarily because of the non-availability of some of these personal protective equipment. Now, one of the major challenges is like many of these are mass manufactured. So you have to wait for a country to manufacture. Since the entire airspace is closed and people are advised to stay at home, factory is not operating, it has become evident that there is a major disruption in the supply chain of these personal protective equipment. In fact, there are many I would say, manufacturing companies, which has now started producing these gloves. In fact, there are Indian companies which have been exporting to Western world. They have been asked to basically keep a stock for Indian use. So there is essentially, I would say, a short supply of these particular components. Now, one of the reasons for short supply is primarily because there are centralized factories and they have a material tier 1, tier 2 supply chain, which has to basically obtain this personal protective equipment, and then they have to use it in the field, especially in the health workers, especially people who are, at the airports, people who are handling large volume of passengers at the airport, even the law and enforcement agency people who are on the streets to basically regulate the flow of traffic, and all those people who come into close contact with people. So they were supposed to wear this personal protective equipment, and even district administrators and even health workers and sanitation people, all those people, they needed this. So suddenly there's a huge demand for the personal protective equipment, and one of the major challenges, reaching the supply chain, especially for the Western world. A majority of the manufacturing is outsourced or offshore, so they were in the major short supply. That is when the 3D printing community basically said that why don't we try and manufacture some of these equipments through 3D printing. For example, 3D printing uses layer by layer approach, where you basically deposit the material one on top of each other through layers. So initially you have to have a CAD model. The CAD model will be taken through slicing procedure. Once you are slicing them into number of layers, you can actually use this models. So let's say, for example, I'll just to show you quickly about a few personal protective equipments. Probably I'll just stop the screen sharing. I'll show some of these parts. For example, this is a simple 3D printed, I would say, face mask. You can actually wear it. So it's like it's a DIY stuff. So do it yourself stuff. This is the one which is commercially available. For example, this is the Louis Philippe cloth based one, which is available, which you can buy from online. Which this is like a stitched one, but you can also use a 3D printed thing, because this is the design has been available. The major problem with this is like you need filters. For example, you can put filters inside, and then you can attach this from the other side. So we have both sides attachment is possible. You can actually make this one 3D printed. This is a 3D printed using PLA material in a commercial, I would say, consumer printer. There are two types of printers available. One is a commercial printer, another is a consumer printer. So the commercial printers are you have to pay and you have to use those supplies. But consumer printers you can actually use. I'll just share the screen. The consumer printers you can actually you can use them. Let's say, for example, for many different applications. So consumer printers are very small scale printers. They are available in many universities. For example, today I can go to any engineering college. I would see a 3D printer there sitting there. It's a very small footprint, polymer printers based on material extrusion technology. People call this as fused filament technology, or sometimes they call it fused deposition modeling. So it's a simple 3D printing process where you can actually use a filament. The filaments gets extruded through a very small orifice called as a nozzle. It's called heated nozzle. There is a small two pinching roller. The pinching rollers draws the filaments into the roller, and then the material gets squeezed through the roller, so that you can actually deposit, like you can say it's like a jalebi making, or squeezing the toothpaste. You're going to make the parts layer by layer. So such printers are there in widespread. I think even in India, many people have those printers at home. In Western world, you have maker spaces nearby where people can go and print something. They have in libraries. For example, if I go to my taluk library or a district library or even my neighborhood library, they have 3D printers made available. So anybody can have a 3D model downloaded from, let's say, a service provider and go and print it. So that is the reason it has become centralized manufacturing. So people started calling for hackathons and makeathons to make some of this personal property equipment. So I think there are hundreds of makeathons by different universities, industries, even accelerators and government. So a lot of hackathons and makeathons have been announced, so that people can design novel, personal protective equipment, so that they can use it for protect themselves from the patients. And one of the things you should understand is it's just not just for protecting you against the COVID-19. Even COVID-19 patients, they may not know whether they are infected because there is a residential period. We call this as the asymptomatic period. So those periods where the patient may not know that he has a COVID-19 infection. So wearing this constantly allows them not to even infect others. So that is the reason why we have to be constantly wearing these masks and personal protective equipments. Now let's just look at some of the shoe covers also. So some of the mask designs, the one that I showed, the one which is 3D printed here, which I showed is having this process parameters. You can see that here there are different designs. The first version uses a rectangular, second uses something like a circular. There are different design variations for the mask. So the model is sliced using an open source software called Ultimate Cura. So the material used is a PLA material. You can use a layer height of 0.25 mm, and then you can have a top layer of 3, wall line count of 3. These are some of the process parameters that normally you will employ for 3D printing, objects. So this is the object that I showed just now was 3D printed using this particular process. So this process is, what we call as the FDM process, or triple F process, fused filament fabrication process. And you can fabricate the one like this, and then you can use it. So only thing is you have to get some filters somewhere available. Probably you can buy a filter. So let's just look at the filters which you can actually use. So here there are different mask designs. For example, this one comes from 3D Systems, which is a supplier of manufacturing equipments for additive manufacturing. Here this fast mask was developed by them. So it's printed using a SLS machine, selective laser sintering machine. In selective laser sintering, you can actually 3D print by using powder particles. You have a polymer powder particles or metal powder particles. You can actually sinter them or consolidate the powder particles by selectively fusing the particles wherever the object falls on in a 3-dimensional platform, so by layer. So this is usually done either through laser or through electron beam. So mostly laser sintering employs lasers, and you have electron beam melting which involves electron beam, but mostly polymer machines uses lasers. Here we use laser beam to basically selectively fuse certain particles. So this particular object or design of a mask is being made using the selective laser sintering process. You can see that there are 2 attachments where you can attach the straps, and you have a filter box and you have a filter cover, and then you can actually use this for different varieties of applications. You can even customize it for your own geometry. Probably you can actually measure your dimensions from your face. Probably you can use a face scanner, or you can use something like, let's say, simple rulers to measure some of the face features and tweak the geometry to suit your design, and then you can 3D print it. So because the customization is possible, you can customize some of the designs which is suitable for your application. So there are different types of mask design. This one is like another design which is available from different kind of the commercial vendors. So you can see that here. So it's like it looks like the familiar commercial N95 mask. You can see that there's a small orifice through which the you can respirate. You can breathe in and breathe out airs. So this is the another application. There are many different varieties of designs that are available, right? So these are some of the things. But what kind of filters we should use? For example, when we 3D print, so the way that we need to basically use this is we need to have filters in between that filter channel. So how do we do this? For example, this is the research which is carried out by many universities. It's a summary of many universities research. This is the open data which is available from smart air filters. If you see, surgical masks have the highest protection, around 97%. And many people also tried with vacuum cleaner bags and dish towels, because we are talking about DIY stuff, because DIY is do it yourself. As I said in our TLC, or Teaching Learning Center, we use the philosophy of low cost 3D printed DIY stuff. DIY means because you are going to make them in your home. If you have a 3D printer access in your college, or let's say in your library, or in your home, or in your neighborhood. So once you are downloading the design, so you can actually looking at the household material that are currently available. Can I just use them for as a filter? So if you see, for example, a small towel has 83%, whereas cotton blend. So you can see different materials have different effectiveness against the 1 micron particle. So if you see, then the highest is like the surgical mask, the 3-ply mask, whereas here silk has the lowest one. So this shows the percentage of particles captured by the filter. So you see that then 40%, almost 40+ percentage of the 1 micron particles are allowed through this silk, so or linen. So it's better to basically have surgical mask or 1-ply mask, which is there. And you also have breathability issues, because once we design something, you also see that you are able to basically breathe through this filter. So the breathability is like so the pressure drop is very high on a dish towel. compared to a surgical mask. So you can see that different levels of breathability for a pillowcase or a scarf or a silk, like pillowcase. So you have to basically look at which one has the zero breathability. That means like you are able to have a high breathability, which is the pressure drop, zero pressure drop. So it's a 0% pressure drop. So you can see that the pressure drop is positive and negative in many different types of material. So you have to judiciously choose something which suits for your application. So this is another interesting product that has become, like mass produced over different 3D printers. Mass produced in the sense mass customized over different people. So you can actually have a 3D printer design downloaded from online, and then you can make it in a 3D printer. So here you can see that there are multiple parts here. So there are two parts. One part can be strapped into another. Then you have a small polycarbonate clear sheet, 0.7 mm thick sheets, and you can actually use a simple nitro gloves, and then you can assemble this face shield onto this what you call a strap, and then you can actually create a face shield. Face shields have become one of the important contributors of preventing splash. Let's say if somebody sneezes it, the particle actually even travel even up to 12 feet. That's what people have studied. So when somebody is sneezing or coughing, so you can actually prevent those micro drops and falling onto your face. So the face mask has been shortage for the first 30-50 days of the COVID-19 inspection. The world was not able to manufacture them quickly. The 3D printing community came to the rescue. So there's a huge surge in the production of these objects after they download the designs from 3D printing. So this is one variation of design which I showed, but there are hundreds of variations of such a design available from repositories like Thingiverse and Shapeways, which you can download. So the design is very simple. So you have to simply download the 3D printed model and then fabricate them using simple PLA or ABS. If you have something like even material elastic, it's fine, but simple plastic materials is fine. Then the polycarbonate sheets are available in your neighborhood store. You can buy them and cut into the shape, and then you can assemble them and then use the simple rubber band, and then you can make the suit. So this one is more little professional. So this is an effort by a 3D printing manufacturer supplier. So 3D printing machine supplier. So you can see that the design is made in such a way that you can even use this to produce durability as well as scalability at the industrial scale. Here you can have many different channels. So you can see that the snorkel 3x walls can be on the one top. You have eyes chamber and then mask side. You have mouth chamber and chin value. So you have so many different varieties of you can say mask adapters which can be used. So this is another important this thing. So you can connect to, let's say, for example, emergency PP adapters, where if you are using them in, let's say, at home, probably you just on a emergency vehicle and then maybe on an ambulance, you can put this mask and connect the ventilators very easily through the available slots, and then it becomes very easy for you to basically breathe as well as protect others from getting infected from you. So these are some of the mask adapters. And also there are other products like face mask buckles. So here, suppose, let's say, for example, you have your face mask. So here, this is coming from Thingiverse. You can see that the face mask can be attached to the rear end of a mask to basically relieve some tension. For example, you see that sometimes your tension on the back band gets very less as you use cloth mask for a long time. So you can actually use this tension relief band. Sometimes you can put it at different adjustments. For example, there are adjustments available here. You can either put it here or put it there. So this is the 3D printed face mask buckle, so which could be used as to release the tension on the back. So this is again available on the Thingiverse, where you can download and 3D print in your home. We also have goggles. Goggles are another important applications of PPE. So here, the frames for the goggles can be 3D printed. So it can be 3D printed using, let's say, if you have a carbon type of printer, or if you have printers like, let's say, resin-based printers, you can print them. Because resin-based printers, you can go for very low layer thicknesses. Let's say there are even low-cost SLA type of printers available. SLA means stereolithography, where you can actually use a liquid monomer, where the liquid monomer can be, let's say, fused, or you can say solidified by exposure to light. So you can have a laser light, or let's say a projected light if you're using mass projection technology. So the light can be projected onto the liquid. The liquid is a monomer, so which is a photosensitive polymer. Once the light falls on it, the polymer gets the monomer gets polymerized so that it hardens in the areas where it receives the light. So other areas still remains as liquid, so that you can drain the liquid and use the parts. So this is a printed out of SLA. So you can also use SLS process to also do this. SLS also can make such a part. So you can use selective laser sintering or stereolithography process, even FDM process to basically make goggles. This is one design that we can see. And also you can use the FDM process. So these are some of the products that so far we have discussed are products which are typically used for personal equipment, not just for health workers, also for any individuals who wish to basically use this at home. But the 3D printing community has also helped to basically use the existing ventilators and make more benefit out of it, or make more use of it. I think one of the things that you should know about COVID-19 is once the patient gets infected, at certain point of time, he may develop pneumonia type of symptoms where he will have difficulty in breathing. So the ventilator should be used, but the problem with most of the country is they didn't have enough number of ICUs, the intensive care units, as well as ventilators for use with COVID-19 patients. So there's a shortage of ventilators. I think there's a huge number of online hackathons. People wanted to develop low-cost ventilators. Many universities, IITs, NITs, IIITs, even other private universities and private colleges, they have made participated in these hackathons, and they developed ventilator parts. So they use 3D printing there. That is a different kind of an application. For example, when you're developing a new product from scratch, so you may want to test out some of the few designs before you commit to a design. So you can use 3D printing as a product development or a proof of concept, developing a prototype. So for prototyping is a time compression technology, wherein if you develop multiple prototypes and fail, so that your final design will be fail-proof. So to do that, you have to basically make one part at a time. So 3D printing has been there for prototyping the medical ventilators, the new ventilators which are under development. For example, many automotive companies have started producing ventilators. There are many, I would say, other industries which have been not in medical equipments, or I would say medical field, healthcare field. They started even producing ventilators. They use 3D printers as a tool for conforming the designs, let's say, or conforming, or let's say, I would say, iterating the design. So they wanted to quickly iterate the design and commit the design. So 3D printing become a very important product development tool for them. And apart from that, even consumer 3D printers, not just the commercial 3D printers or commercial developers of or universities which are developing the ventilators, there are people who pitched in to use one single ventilator. With the help of one single ventilator, they could actually treat two patients, or even they could share one ventilator with two patients by having a splitter. So this is called as a flow splitter or brick ski tube. So you can use something like a nylon adapter, or maybe it could be printed using simple PLA or ABS. But only cross-contamination is one of the issues that has to be addressed, because when the same ventilator has been used for two patients, it may lead to cross-contamination. But when the two patients are having infections and they are in the same stage of the disease, you can actually use this flow splitter configuration. But the availability of the flow splitters again was limited because the entire transportation sector, logistics sector came to a standstill. So you are not having enough access to these parts. So people started designing using 3D printing. They started making these parts and then testing it, and then even we made few parts and tested it in our laboratory and give it to the hospitals nearby to test it using a single ventilator. So the design configurations is something like this. We have a simple tube. One tube comes in. So I'll show how this is being done. So you have a splitter, you have a portable Y splitter, and you have a ventilator. For example, there is also a different diameter, flow limiters. These are called flow limiters. So you can actually have 11 mm, 12 mm, 13 mm, 15 mm, 16 mm. So which has different cross-sectional areas to allow different kinds of flow. So it limits the flow. We call this as three-dimensional rendition of flow limiters, because we are able to see how the flow limiters can limit the pressure of the flow which is happening inside the, so that we can actually control or regulate the pressure inside both the regulators. So you can see the Y splitters. This is another type of splitter. The previous one we saw is a T splitter. In the Y splitter, you can see that you can actually have the two connections. See, for example, this connection and this connection goes to the two patients. Here, this connection goes to the other patients. The dual explanatory limb wall. So you can see that. So how the splitter can be used for using this. This is a differential multi-ventilation. This process is called differential multi-ventilation. Here you can actually have the flow happening in 2 tubes instead of 1 tube. So if you use a splitter like this, it can be simultaneously used. So so if you have 100 patients with 50, let's say ventilators, you could have treated 100 patients. So the short supply of ventilators has been overcome initially, because it takes certain time for the new ventilators to be manufactured, transported, and then commissioned into the tested and commissioned into the hospitals. So normally people wanted to basically pitch in and then produce this splitters using the 3D printer and supply to the hospital. So initially there have been huge examples of universities, like universities in Western as well as Indian universities. For example, there are a lot of private universities in and around Trichy and Tamil Nadu. They have started a process called as crowdsourcing of producing these parts through the 3D printers, which are available in that area, so that they could reach out to the hospitals and give this to the healthcare workers, doctors, so that they can use it and test it on patients. So they could use the same ventilators for 2 different patients. It's addressed the issues very easily. So this is a splitter example which is shown here. Here you can see that there is a inspiratory and expiratory limb, and there is a 3-dimensional 3D splitters. For example, this one and this one goes to the patient A, and this one goes to the patient B. So you can see that the same ventilators are again another example of the same. So by using this splitter, so this is the one which is 3D printer. So this 3D printer is splitted, because you normally get these supplies, 2 or 3 supplies along with the ventilator. So normally we'll have a supply of these tubes and all, but only the splitter may not be part of the supply. So 3D printing community started 3D printing the splitter. But there are major problems with this printing. We have faced issues such as orienting, because whenever you have a cylindrical object, one of the major issues with 3D printing is support structures. When you're trying to build 3D printed objects, you need to build support structures. Support structures helps you to keep this object overhangs when they cannot be self-supported. For example, in powder bed fusion, when you are trying to create an overhang, so you would be able to basically create something like without support structure, the existing powders, or I would say the sheets can be supported without. But in material extrusion and other process or liquid-based process, where you need to basically build support structures. So for cylinders, when they are made in layer by layer, so you need to build support structures. The removal of support structures in these chambers become a little difficult. But there are certain polymer printers which you can actually, by carefully orienting them, you can completely avoid, or you can avoid a little of support structures. So we are able to basically remove the support structure, or we could be able to build without support structure by careful orientation of the cylindrical parts. But this part is a little too complex to print, because it has got 2 different angles of cylindricals which needs to be fabricated. So I think you can find out the best orientation. The orientation which you don't need to build any supports. For example, if the axis of the let's say cylinder is oriented perpendicular to the build platform, so you don't need any support structure. But again, there are 3 different angles, so it is very difficult to know which cylinder you need to orient in which orientation, because you cannot avoid supports at any cost for these kind of parts. So it becomes a little challenging for people to 3D print in the 3D printers and remove supports and produce them at high quality. Also, they have to remove the supports because they may be getting contaminated with a small particle goes to lungs, and also it becomes a very important process. So this brings me to another question. For example, many of the medical products, they need to be certified by ICMR in India as well as FDA in other countries like US and all. So Food and Drug Administration. So FDA issued a very important, I would say, approval in the early March 15 to March 19. Even before that, I think there was first version of the document came into circulation in March. So the document clearly says that if you are printing some of the parts using 3D printers and use it, so they gave an in-principle approval of some of the designs. For example, if you need to obtain certification for any health-related equipment, it's a lengthy process. But because of the pandemic, an ongoing crisis, and because we are losing too many lives, FDA has categorically mentioned with some clauses, they approved in principle some of the 3D printed devices to be used in hospitals. So they gave an in principle approval based on the need and based on some certain tests. You can actually use them in some of the medical applications. So for US, some of the 3D printed applications have been certified by FDA themselves, and they were in use even today in some of the hospitals. So these are the print settings for such a parts. For example, here these are the 3D printed ventilators. Here mostly you can use a biocompatible filament which doesn't have cytotoxicity, and also it doesn't have particles which could cause harm to the lungs. You can put them through sandblasting or even through cleaning, and then you can prepare the parts for medical use. So we have to use 100% infill for strength as well as for leakage, and also the layer thickness is 0.2 to 0.3. And for some of the printers, we have carefully oriented in such a way that there need not have to be have any supports, because the angles of the prints are so decided in such a way that you can print them without supports. But there are other processes where you can have problems in supports. For example, if you are using SLS kind of process, you don't need to build any supports. Even for material extrusion like the FDM process, in certain orientations we are able to build without supports. So these are some of the 3D printed vent splitters. So these are some examples coming from different sources. You can see that there are very many different variations of the same design people have made, and then they mass manufacture and supply to the hospitals. So this is another example. So this we call as the Venturi wall. So here, if you see, for example, this is a Venturi wall. I'll just quickly show the part. So just stop the screen sharing. So screen sharing, I'll show some of the parts. So this is the part which is made using, let's say, SLA process. It's a resin process. It's a resin-based printing. We use a liquid resin and 3D printed. So I'll explain about this part. So this is the 3D printed Venturi meter. So here, these are several variations of the design is available online. For example, even companies in and around Chennai, they started manufacturing it. They produce several variations of the same design. In fact, it is like open source design. People have been designing these parts online for a very long time. So, so we can actually have these kinds of parts. These parts are very useful in controlling, I will say, the flow and pressure, because you see there's a constricted passage in between. So you see that this part is like there's a small contraction in the passage. It regulates the flow. I'll tell you about the different variations. So what is the flow rate that you can plan for? For example, 40 liters, or what is 60 liters, or what is the flow rate that you can use per second. And then you can also understand the diameter variation. So there are 7-8 different variations have been made and tested for variations in the flow. It creates a little bit of pressure. So we'll see some of the applications of this one a little later. So I'll just share my screen again. So yeah, so you're able to see this parts. So these parts are called Venturi walls. This is used in respirators. So these are parts which are made by 3D printing community. So across the world. So for example, these are some of the walls which are printed by an Israel company in metal. These are polymer 3D printed, and these are SLS, selective laser sinter 3D printed. These are printed using FDM process. This is printed using SLA process. You can see all the manufacturing, additive manufacturing techniques have been used in producing Venturi walls for respirators. So this is, here there are no rods. The layer thickness used is 0.2 mm. So the one that I just showed, we used the material of ABS as well as PETG. And we also didn't use any supports for building these parts because the cleaning of them becomes a little difficult. So we designed many variations of the part. So this is the actual 3D model of the part, and which could be used for respirators. So what is the use of the respiratory wall? This is another example of respiratory walls, which you have seen previously. You can see that here the PLA filament is used. This is called Charlotte wall. So here it's a nozzle temperature that we use is 205. The diameter of the filament that we use is 1.75. We use the PLA filament. So there are many online examples of such parts, different variations available. You can also pick up one design and modify it and suitable for Indian patients, or maybe for Indian conditions, you can redesign them and then use them appropriately in some of the Venturi meters used in ventilators and other places. So another important thing that COVID-19 has demanded is testing. I think most of you are aware that testing the patients is becoming extremely difficult. So, for example, one of the tests that the way test is they put a nose swab, take samples from the nose, and then they test for COVID-19. So the PCR test is usually collects samples from the nose. So people felt shortage of these devices because the swabs. People never thought that such a large number of tests needs to be done. For example, you must be aware that US has conducted the largest number of COVID-19 tests across the world, whereas India is also doing. In fact, Tamil Nadu is doing a lot of tests compared to many other states in India. So how much of people to be tested and all is a different question. It's a medical thing, but here we are talking about printing some of the nose swabs. So many nose swabs are to be printed. So here the swabs may be sterilized based on the guidelines. So you can actually put it in the pre-vacuum steam sterilizer for 30 minutes at 121 degrees, and you can autoclave after the manufacturing is done. So you can actually put into the temperature. For example, some of the polymers may not withstand certain temperature. You have to have high temperature polymers, or sometimes metal is also used. For example, this is a nose swab manufactured through a commercial facility, and then they are made available to the local community and hospitals. They used a 6-inch with let's say 15.15-inch head diameter. So these are some of the surgical techniques which are people use to basically collect the samples. So these are nose swabs, and these are nasopharyngeal nose swabs which are for testing the sample. So there are a lot of examples available. So this is the varieties of designs people have made. For example, one of the basic idea that I discussed previously is about the ability to use lattice structures. For example, here you can see very complex lattice structures are being made so that it can collect the sample very easily without the help of even cotton. So that it can be just thrown away. So you can see that this particular it can be recycled without any difficulty. After this is done, you can actually completely incinerate, or you can recycle them. After incineration, you can take out the polymer and then again make the same set of experiments. So it's like very easy. You can see different designs have been made. Their effectiveness in capturing the sample and the viruses has been tested for many different patients. So these are some of the examples. We'll just now discuss about another important infection route, which is called self-inoculation. Self-inoculation is something like, let's say, for example, self-inoculation is like we infect ourselves. For example, we travel a lot in the morning to get some, let's say, groceries or vegetables. We go to the market, and sometimes we may also have to go to the hospitals. Sometimes even the health workers who are working in the hospitals, they're exposed to viruses all the time. There are surfaces, we call this as fomites. When you touch them, your hand can get infected. So because when you touch some objects, maybe a glass that somebody used, or maybe a lift buttons, or maybe a door handle. So once your hands, so the problem is now whenever we go to the grocery store or whenever we go out, you immediately come back without touching any surfaces. You go and wash your hands, then it's fine. But the problem is sometimes we also touch our face. So an average human touches his face, more than 50,000 times a day. So even more, some people even touch more than that. So essentially, to avoid touching these objects and then touching your face. So once you get the infection from your other parts of body, self-inoculation, what we call as is the infection you transfer from one part of the body to another part of the body. For example, if you touch your face or like your nose or your lips or something, so essentially you are going to get infected by the virus. So people have came up with some of these devices which helps them to basically stay protected. For example, switching on the lights or switching the lift buttons, door handles. So a lot of personal equipments have been developed. I'll quickly show some of these equipments. For example, one of the equipment is door opener. So this one is a finger cap. So you can actually put a finger cap and use it. So you can actually, once you come back to home, you can just throw away these finger caps, which contains infection. So this is a door opener. So you can use a door opener like this, and then you can sterilize them once you come back to home, because you are prone to touching your face often. So you can use this, it's an ergonomic door opener. It's a no-touch door opener. You can also, people also call a safety key and things like that. So this is another design. So another design is people have also developed door handles, attachment to the door handles, which you can use. For example, this is one example of a design of a door handle from some university. So you can actually use this to open the doors instead of touching the door handles. There are also foot-operated designs. You can actually use your foot to operate. I think you have seen that there are in many public places, people started giving taps for washing your hands, and also soap, dispensing soaps The problem is most of them you need to again touch them. So many people touch those surfaces, you will get infected. So foot operated devices have been made. So 3D printing has been in one of the very important uses of door handles and things like that. So you can see there are many orientations in which this is built. So this is one example. This is another example of a door handle design. So you can see that you can actually use your forearms, or you can use your arms to, without using the touching the surfaces. You can actually use your back arms also to open the doors and use this. So again, another design, so which is little tricky here. It becomes really difficult to maneuver this in different directions. But this is one variation of the door handle that people have tried out. And another design you can see. There are many different such designs which are available. So which could be basically fitted into the doors. So sometimes you have to turn it, sometimes you have to release after turning. So it becomes extremely difficult to design something which can be fitted into the existing components. So 3D printing came to the rescue. People started crowdsourcing these parts and then fitted them into the public hospitals. So many hospitals received 3D printed door handle attachments so that the doctors can open them without touching the door handle, so that it becomes less infected. So even though they are disinfected very often, but the people who are moving in and out of the rooms, they may get infected by touching those door handles and door knobs. So it becomes easy for somebody to design something else. These are some variations of the same design which you can see. Right? So these are some of the variations. You can see that some are cylindrical narrow, some are cylindrical wide, some are rectangular wide, and some are rectangular wide. And these are some of the designs which are available online. So all these designs are available online. For example, you can go to thingiverse.com, you can go to shapeace.com, even other public repositories that you are aware. You can share it in the chat here so that people can go to those places and download this and print it at your home if you have access to 3D printer, or give it to your students at universities probably if they are available. Or maybe you can go to the lab if you have access to the labs, you can print something like that. For example, I will show you one of the door handles that we 3D printed and tested. We have some videos, but I will not be able to show the videos right now. I'll quickly show some of the door handles that we 3D printed and tested it. So stop screen. So you can see this door handle. So this actually has a two-part. So you can actually put it onto the door handle like this, and then you can put the bottom up. You can screw it up so that you can actually operate it like this. So once it is attached to the doors, so you can actually move the door handle like this. You can use the foam arm. So it's very easy to basically not touch this. So only this part you will often touch in your face. So it becomes extremely easy for you to basically move the door handles without touching them. Even you have if you have more, you don't have to apply more force, because this is like a lever concept. So you apply the force at the end, it becomes easy to operate the door handle. So you can 3D print some of them, or you can, whatever material available to your home, you can even make it without, even if you don't have a 3D printer accessories, you can make something out of, let's say, polyurethane or something which you have a molding clay or something like this. So you can actually do a lot of this. Right? So I again go to the screen and then I'll share the screen. So I think you can see that PPT hopefully. Yeah. So these are some of the door handles. So I'll give you some process parameter for you to 3D print them. So layer thickness is 0.2 microns. The speed that we used is 50 mm per second. And the bed temperature, you can use something like 60 degrees per centigrade. Retraction distance is 6.5 mm. So these are some of the process parameters. They are available in the YouTube live channel. So anytime you can come back and see these process parameters, you can print it at your home or in your 3D printer. So this is again another one, which is again 3D printed with the same different process parameter. This is the previous one was a PLA material. So this one is like ABS material. So you can see the ABS material here. You can also use PETG. So you can use PETG. These are the process parameters for the PETG. And I will show you quickly some other applications, and then so here you can see that we have some 3D printed sanitizers. We'll just quickly show you some of the sanitizer holders and things like that. So yeah, so you can see some of the door openers and door handles. A lot of designs are available. You can quickly go to online, get something like that. So you can see there are hand sanitizers which can automatically dispense sanitizers. You can use simple Arduino module or simple ultrasound sensors to you have a near so people go near and you can sense the people, and then you can start dispensing automatically and things like that. a lot of online application of sanitizer holder is there. So these are some of the 3D printed stuff from DIY things. You can see some of the keys, door openers and things. There are many different designs available in Thingiverse which you can download and use it. So these are many different applications, right? So there are so many different applications. This is the one application where we have a keypad, where you have a fidget spinner and all those things. So you can see many different applications. So these are printed using PLA, ABS, and PETG and all those things. And before I conclude, I would like to say that we have another conference which is coming up. I'm also another member of the scientific community. But only problem is it's got only 2 days, so you can submit. There's a special session called Additive Manufacturing Meets Medicine. There's a special session on anti-corona aids and devices, so to fight virus. So you can write a 2-page manuscript and submit that by May 18th. So you can. It's a virtual conference. You can attend. So this is my acknowledgement. These are my lab members. And the slides are prepared by some of my research scholars like Hemnath, Madan Gopal, and Regina. I like to acknowledge the team. So thanks, and I will give back to the head of the department at SAEC Engineering College to give some closing remarks. Thank you very much. I'll just stop sharing the screen right now. Yeah, thank you. Yeah, so there is some request for sharing the screen. I'll share the screens. I'll share the PPT so that they can mail you the PPT to all of you. So we'll give the PPT to all of you. To head of the department at SAEC Engineering College to give some closing remarks. Thank you very much. Just stop sharing the screen right
now. Good afternoon, everyone. So on behalf of SAEC Engineering College and all the participants, I thank Dr. K. Senthil Kumaran, sir.
Yeah, so there is some request for sharing the screen. I'll share the screens. I'll share the PPT so that they can mail you the PPT to all. So we'll give the PPT to all. To head of the department at SAEC Engineering College to give some closing remarks. Thank you very much.
Yeah, good afternoon. Good afternoon, sir. Really, we had a very wonderful session.
Good afternoon, everyone. So, on behalf of SAEC Engineering College and all the participants, I thank Dr. K. Senthil Kumaran, sir. Yeah, so there is some. A very wonderful session, everyone. So, on behalf of SAEC Engineering College and all the participants, I thank.
Good afternoon, sir. We had a really wonderful session. Special thanks to Dr. K. Senthil Kumaran, Professor, Department of Mechanical Engineering, Indian Institute of Information Technology, Design and Manufacturing, Kancheepuram. Really, we had a very wonderful speech, sir. So we got many ideas about 3D printing and how it is useful in this pandemic situation, COVID-19. So as you told, really in next 4 or 5 years, it will be rocking out all the technologies. As you told, it will be playing a vital role in the mass production also. And just before 15 or 20 years, if we say internet, that is everything will be available in your hand. I don't know how much of them have believed. And surely in the next 3 or 4 years, I think as you suggested, homemade printers will be available, which can be used in every house or even in the nearby places and all. So in any emergency situations, just by downloading the design, we can print the products whatever you want if you are available with the materials and all. And here also, so as we see in this pandemic situation, we know many doctors, health workers, and the people from police department and power production workers, they are sacrificing and they're taking a risk a lot to save us, to safeguard us. We are in our home safely, but in this real situation, as a technical people, it is our role and responsibility to contribute to the society also. So here, this 3D printing technology, so here really it is a very wonderful technique. And Dr. Senthil Kumaran has explained it clearly about what are the various products which are developed during the situation, such as the masks, goggles, and again the concept of do-it-yourself. It's a wonderful. It is amazing, and so that based on the measurements of your face, you can easily build the mask to which suits you also. and just we have to replace the filters. And we also discussed about the various ventilators under the ventilator circuit splitters. Very complex designs are easily made using this 3D printing technology. And some other new things also which we just got information is about the finger caps, the door handles, etc. And really, so we are having a widespread, particularly in this situation. So we have to use the technology and we have to protect ourselves from this pandemic spread. So we discussed about the various things which are useful, and also he discussed some of the challenges in the 3D printing, such as the requirement of the support structures, etc. But on overall, if we see, this is really going to be a big boom for us, and using that we will be surely utilizing this technology a lot. Very much thank you for your presentation, sir. And tomorrow morning, again by 9 a.m., we'll be having the second session. It will be handled by Dr. T. Ram Prabhu, scientist DRDO on additive manufacturing for metallic parts. And hope everyone to join us tomorrow by 9 a.m. Thank you.
Thank you, sir. Thank you. Thank you.